Hi everyone, this is Wen. In today's video, I'm going to continue the part 2 of the video to introduce the Cuda implementation of neural network. So before we delve into the code, I hope to give you a brief review on the structure we're going to implement it. So here is a highlight of the structure. We are going to have 4 layers. Basically, we have the linear layer, relu layer, and sigmoid layer. In the first video, we introduced a relu layer and sigmoid layer with necessary classes. And from this video, I will cover the linear layer as well as the rest of classes in the code. So let's delve into the code. And first of all, I hope to introduce one special header to you, which is called an exception. And this is very useful to catch the exceptions for the Cuda code. And for every Cuda operation, it will return a Cuda error message from every Cuda operation. So basically, we can get that from this method, Cuda get last error, and we can compare with this message with Cuda success. If it is equal to success, that means it has been successfully executed. Otherwise, we will get some exception message, and we can output exception message and with a customized message when we call this method. So this is very useful to catch the Cuda exceptions. And let's get into the linear layer header. And firstly, in the header, it declares some methods for the linear layer. Basically, at top we have include several namespace, which is for the testing purpose, and can be used for multiple namespace this class. And also we have the linear layer. We define several variables as we did in the previous class. And for example, we have the output like z, and we have input a and the dA. dA is the input for the back propagation. And we also declare the method, for example, like the initialize bias with 0 and initialize weight randomly. And this all of this method will be initialized or will be defined in the Cuda file. So first of all, let's give it a brief look at. We also have like the function constructor and deconstructor, and we also have the forward and backward propagation. And we have some extra method. So let's take a look at the Cuda file directly. And before delving into the kernel code, I hope to go through the host code first. So in the host code, we have a function constructor, which is going to accept 2 arguments for a linear layer. The first one is the name of the linear layer, and the second one is a shape. So you can see from the shape, we're going to input a shape class instance. So this shape class has 2 dimensions, x and y, and basically we are going to have the weight of the w, which is going to be the same shape as w underscore shape. And also we have the bias, which is going to be the y dimension of the shape, and then the y dimension of this bias will be 1. So it's basically a vector instead of matrix. And then we have the allocated memory. We have the allocated memory for both bias and weight. Also, we initialize the bias with 0, and then we initialize the weight with randomly. And let's look into this code directly. I think it's right below. So followed by the constructor, we have the deconstructor. So here we have the method to initialize the weight randomly. And basically the weight matrix will be initialized with a value that has distribution of 0 mean. And the standard deviation equals to 1, and which is going to be the normal distribution. So this is how we initialize a weight. And also for the bias, we will simply initialize to 0. But all this code happen on the host, so we have to copy the the data to the device. So both of them will be used to copy host to device, whether the W or B. Even though the B is a vector, we treat it as a matrix. And then we have the forward method, which is going to do the forward propagation. And what is the input? The input will be A. And remember, we have the before I show you the before we move forward, let me show you one thing about the linear layer. So basically, this is a formula of the forward propagation, and which is Z equals W times A plus B. So we have the A as the input, and every time we output the Z as the next input of next layer if we have several linear layers concatenate with each other. And furthermore, we have the backpropagation formulations. And here we have the dA, which is the arrow introduced by the A matrix. So what we will do is to backpropagate this dA to the preceding layer. So that means every time we backpropagate this dA to the preceding layer. But we also need to do the derivative on the dW and dB, even though we don't backpropagate these two. But we have to use them to update the weight matrix and update the bias matrix. So you can see the formula is quite similar. We always have this dz as a backpropagated derivative from the coming layer. So this is when we do the backpropagation. So this is from the coming layer, and we output the dA to the preceding layer. So this is the basics for the linear layer. So that is brief introduction, and let's get back to the code. So as you can see, we are going to allocate the z because the z will be the output, and we first initialize a shape instant of the shape of x and shape of y, and then we allocate the memory for the z, and then we do the compute and store layer output and has a as input, and basically this one will be the method right below, and which is going to take the matrix A as input, and then we will call kernel. But before the kernel, we will initialize a two-dimensional grid. It is quite a little bit different from the example we were talking about in the ReLU function and sigmoid function, because they all take one-dimensional grid. But here we take two because we're doing the matrix calculation, and that will be much easier if we have two-dimension grid, and we can find the corresponding threads easily. So here you can see the number of threads, number of blocks is 8, and each block has 8 threads. So that is basically how you do. And then we call the linear layer forward, and so this is a kernel we are going to look at. So if we take a look at the kernel code, and this is what we do, the forward propagation, and the formula is same as z equals w times a plus b, which is very straightforward as what we are going to do. And how we are going to manage the calculation, and basically we are going to manage the calculation like this. If we are going to calculate a matrix A by matrix B, and then we are going to use every thread to calculate a single point in the result matrix. So for example, for the first element in the result matrix, we are going to use one thread to calculate this point. So what it will happen is it will take the first row of the matrix A and first column of the matrix B, and it will calculate the multiplication of these two, one row and one column, and add them together and get the first element of the first row and first column in the result matrix. So this is how we calculate. So you can see there is a for loop, because we have to loop through every element in the first row of the matrix A and loop through every element in the first column in the matrix B, and then add them together after multiplication. So you can see there is a for loop. We are going to loop through the row and column and multiply them together and add them into single value. And finally, we will, based on this z value, we are going to add the bias as well. And initially, the bias will be 0, but will be updated after we do the back propagation. So this is a forward propagation. And then we are going to look at the back propagation. And back propagation, we're going to give you input as dz, and then we are going to have the learning rate. And basically, there are three things we are going to do. And the first one is, this is one that is, we're going to check whether the memory is allocated or not. If not, we're going to allocate the memory for the A, for the DA, because the DA will be an output that will be propagated in the preceding layer. And we take the DZ as an input, and then we're going to do the three things. The first one is we're going to compute and store the back propagation arrow. And let's take a look at the code here. So if we do the compute and store back propagation arrow, and we're going to take the DC as input, and we define the same 2D grid, and then we're going to call the kernel that is going to do the back propagation. So if we take a look at this one, DZ is the input, and DA will be the result that will pass to the preceding layer. So the DA will be the arrow that introduced by the input A, input matrix A. So what we are going to do is we are going to use the formula we just saw in one of the screenshots. So basically here we're calculating this formula. The W weight matrix transpose times DZ will give you the DA. So basically we'll do the same thing. One thread will correspond to calculate one element in the result matrix. And then we're going to calculate the DA and from this accumulated value. And this DA will be propagated to the preceding layer. So that is how the back propagation do. And then we also need to update the bias and the weights. So if we take a look at the bias, update the bias, and we're going to see that we are going to use a one-dimensional grid instead of 2D, because bias is a vector, right? So we only use the vector one-dimension one-dimension grid. So when we call the kernel, we are going to look at the so when we update, I think this is a kernel code. So if we take a look at the kernel, we are going to update the bias, because the bias also introduces arrow. So this is how we calculate the arrow based on the bias. This formula is how we calculate the arrow that introduced by the bias, and then we're going to update the bias based on this arrow. So all the things that depends on the DZ. DZ will be the input as well. So the weight will be similar to the bias. We also need to update the bias of the weight. Update the weight based on the DZ and the learning rate we have. So basically, let's take a look at the kernel. In the kernel, we're going to do the similar thing based on the formula we present in the screenshot. And what we're going to do is we're going to adjust the learning rate. We're going to adjust the weight based on the learning rate times the D weight. We're calculating from this from here over here, and we have to divide by the dimension, basically the dimension of the batch, and then we times this update value, and then we minus this, and to get the new updated weight. So this is how we update the weight and update the bias. And the other class are very simple, like the get dimension of the x, get dimension of y, and get weight matrix, and get bias vector. So this is a linear layer. And next, let's look at the neural network. I think in last video we also look at this neural network, but I hope to go through it again. So basically, you can notice that in the forward propagation, we always have the same variable z as the input for the forward propagation for one layer, and then we save the z to this kind of global variable, and then we put into another layer. So basically, this z will be the input of the next layer and will be the output of the previous layer. And same thing happens on the back propagation. We are going to use an arrow to always save the previous layer's output and then use this as input for the next layer. So every time we will change the rule either from the forward propagation and also from the back propagation. So this is a neural network. And then let's look at one more class, that is a BCE cost. So the BCE is basically the binary cost entropy. This is how we calculate the binary cross entropy. Let me pull up this screenshot, and this is how we calculate the BCE, which is this formula. And then we also compute the derivative of the BCE by this formula. So the y hat is the y hat is a predictive value, and the y is a ground truth. So we are calculating, we're counting whether the predicted value is the same as actual value, which is a ground truth. And this one will give you the BCE and derivative of the BCE. And the implementation is also simple, and just implement the formula we just saw in that screenshot. So this is basically the cross entropy part. And finally let's look at the MainCU again. So this is where the class where the main entry for the whole project. So but before that, I think we need to take a look at this coordinate data set as well, because this is also very important. Basically, this is how we generated the data to train and test. So basically, we're going to randomize some data, and then we're going to check whether this value is greater than 0 and the value is, this part is greater than 0. So what does this mean? Basically, let me pull up another screenshot. So basically it means whenever we have in the coordinates, we have the first and third quadrant, we're going to categorize them as a same category. Whenever we have the second and fourth quadrant, and we're going to calculate them as another category. So this is two categories, how we define them. So basically, this is how we randomize our data and randomize and also classify them into two different categories. And this will be the data we're going to use to train and test our project. So let's get back to the main. Basically, firstly, we're going to have this coordinate data set, and we're going to have the 100. This 100 is going to represent the batch size. That means every batch has 100 records, and then we are going to have 21 batches. So if we took a look further, we're going to notice that for every epoch, we are going to have 20 batches for training and 1 batch for testing. And for that testing, we're going to get the accuracy score for every epoch. But I think we are going to print the cost every 100 epochs. So even though we can calculate for every epoch, we only print out for every 100 epochs. So that is how we do that. And here you can see we have the 1,000 epochs, and we're going to do the forward propagation, and we're going to do the back propagation, and then we're going to calculate the accuracy for every. So you can notice that get number of batches minus 1. So that means we're going to get the last batch for the accuracy calculation. And when we calculate the accuracy, we're going to call the compute accuracy, which is here the method that is going to count the number of correctly predicted value and divide it by the size of the output vector. So that is how we straightforwardly calculate the accuracy. So, and finally we're going to divide them by m. M is the size of the batch. So this is pretty much, I think, for the whole project. So I hope these two videos have already given you some insight how the implementation has been done in the Cuda for neural network. So based on this code, we are able to further extend and make it more complicated neural network. Maybe you can add some more sophisticated layers, and other than these 4 basic layers. So I think that's pretty much for today's video, and I hope you guys enjoy, and until next time, happy coding. Thank you so much for your time.